This week, AI world models are moving from passive video prediction to controllable environments where agents act, robots remember consequences, and synthetic experience trains policies. That matters because progress is no longer just visual realism. It is preserving the state, uncertainty, and action consequences needed for reliable behavior. From MIRA's 4-player Rocket League simulation to Alibaba's digital teleoperation, with ideas adjacent to NVIDIA Cosmos and Meta's V-JEPA 2, the shared direction is clear. World models are becoming data engines and control interfaces. We'll see what makes them fast and coherent and where impressive benchmarks still fail to establish real-world reliability. Let's explore the first paper, 2607.05352. MIRA, from teams at General Intuition, Qtai, and Epic Games, introduces a multiplayer world model that simulates 4 interacting players in 2v2 Rocket League, rather than treating other agents as background scenery. Trained on 10K match hours generated by Nextobots, its approximately 5B parameter flow matching transformer predicts all players' futures jointly from synchronized views and action streams. The model operates in a representation autoencoder built on frozen Dynoff 3 L features, using a 10 Hz latent space, diffusion forcing for exposure to imperfect rollout context, and progressive self-distillation for fast sampling. With streaming KV caching and a 20 latent context window, MIRA generates 20 frames per second on a single NVIDIA B200 GPU. Distributional quality remains stable through 5 minutes, despite training on short clips. The latent design is crucial. At a 4-second horizon, MIRA reaches GFID 10.7, compared with 104.9 for a matched plain pixel space model, while its action recoverability ratio reaches 0.91. Multiplayer conditioning also improves shared world coherence, keeping cars, ball trajectories, goals, demolitions, and HUD events consistent across 4 viewpoints. The authors find that pre-trained visual features improve generative stability even when a from-scratch codec reconstructs sharper images, and that diffusion forcing substantially outperforms teacher forcing. Remaining failures include rare uncommanded boosts, drifting clocks and scores, and incorrect behavior for underrepresented events such as a stationary ball. Let's explore the second paper, Kairos, a regret-aware native world action model stack for physical AI. Kairos proposes a regret-aware world action stack for physical AI, arguing that robots need compact control-sufficient states, not pixel-perfect simulations that preserve object state, contact conditions, task progress, action consequences, failure risk, and deployment uncertainty. Positioned alongside NVIDIA Cosmos, Meta's V-JEPA 2, and OpenAI Sora, Kairos unifies understanding, generation, and prediction through a shared latent state, using video deity and action deity to jointly model future visual and action tokens. Its cross-embodiment data curriculum progresses from passive internet video to human behavior and robot interaction, while hybrid linear temporal attention combines sliding window attention for local contact dynamics, dilated sliding window attention for mid-range events, and gated linear attention with gated deltanet for persistent global memory. Flow matching, DPO-style regret alignment, time-step distillation, quantization, and hardware-aware kernels target deployment efficiency. The compact 4B model scores 9.3 on World Model Bench Robot, reaches 96.1 average success on RoboTwin 2, and achieves 90.8 on Libero Plus when future video and action prediction are jointly denoised. Its 4-step distilled generator reduces sampling cost, while Kairos 4B requires 2.3 pflops for 720 p5-second inference. At 15 seconds, it records a 79.9 PAI bench overall score. These are proxy results, rather than proof of lower real-world regret. Imagine-to-real rollout, correlation, counterfactual action validation, failure prediction, safety filtering, recovery learning, and real robot policy improvement remain future evaluations. Let's explore the third paper, RIN-World Teleop, an action-conditioned world model for digital teleoperation. RIN-World Teleop, developed by Alibaba Group's Damo Academy, the Hong Kong Embodied AI Lab, and CUHK, proposes digital teleoperation. Instead of moving a physical robot, an operator's 21 joint hand-posed stream conditions, a robot-centric world model that generates egocentric execution video and synchronized robot actions from a single reference image. Built on WAN 2, 2, TI, 2V, 5B, the system combines depth-aware skeletal rendering, progressive pre-training on human egocentric video, followed by robotic adaptation, and streaming autoregressive distillation with causal flow matching and DMD. Its causal student generates 40 frames per second on a single NVIDIA H100 GPU, using 4 denoising steps and a KV cache, enabling interactive control. Training includes 1,800 real-world bimanual demonstration episodes, while large-scale human pre-training supplies manipulation priors. On the EgoDex benchmark, the full model reduces FED to 550, compared with 1,223 for direct supervised fine-tuning of the same base model. As a data engine, RenWorld Teleop improves downstream policies. Augmenting Pi 0.5 or Pi 0 with 300 synthetic episodes raises lid placement success by 20%, and Physical Intelligence SPI 0 trained with 300 generated episodes and no real data reaches 82.86% on block pushing. These results suggest that digital teleoperation can scale robot learning data collection without robot hardware, 3D assets, or repeated physical environment resets, although per robot fine-tuning and weak performance on deformable or liquid interactions remain limitations. That's a wrap on today's AI paper highlights. Thanks for watching.